So in this problem we have this solenoid, and we know the number of turns per unit length. And so because we know the number of turns per unit length, we know the magnetic field inside the solenoid, at the center of the solenoid. It's given by this equation. So it's this value of the magnetic field inside the solenoid, but they tell us that at the edge of the solenoid, the magnetic field is half as big. So we divided by 2. So that's the value of the magnetic field at the edge of the solenoid. And if we have a ring out here, and we want to know the induced EMF in that ring, well, the induced EMF is the change in magnetic flux with respect to time. The flux is the area times the magnetic field. So the area is this area where the magnetic field exists. It's times the magnetic field in that area, which is this magnetic field is just that magnetic field produced by the inner solenoid. But we take the derivative with respect to time. So the induced EMF is given by this quantity. Now, of course, the area is just pi r squared, or r2 is this the radius of this little circle. So we know the induced EMF in the ring, in the big ring. So this induced EMF is just this equation here. And if we want to know the current in that ring, we just divide the induced EMF by the resistance of that ring. So we take the induced EMF and divide it by the resistance. So we just write down the equation we have for the induced EMF and divide it by resistance. And that's the current in the ring. So the magnetic field at the center of this ring that's produced by this current, we have the ring with current going around it, then at the center there's a magnetic field produced by this current that's going around the big ring. So we can calculate this magnetic field using the Biot-Savart law, and that tells us that the magnetic field at the center of the ring is given by this equation, where we know the current that we have to plug into this equation. The radius is the radius of this big ring. And the integral is easy because this integral is just the integral of ds, which is just the circumference of the ring. So we can plug in, here we have the integral of ds, that's just 2 pi times the radius of the ring. And then this simplifies, of course, to this term right here. And the current in the ring, we know it. We already calculated it before. So we plug whatever we had for the current, which we calculated by finding the induced EMF and dividing that by the resistance of the ring. So we had before an expression for the current. We plug it into this equation that we have here that depends on the current. So now we're going to take this equation, and this radius is the radius of the ring, which in the problem that we have is called R1. And now we plug here the value of the current in the ring, which was this expression we had calculated before. So now this is the magnetic field in the center of the ring. So let's look at what's happening. There's the solenoid like this, and the current is going in this direction, let's say, so the magnetic field inside the solenoid points that way. So in this big ring, the current points in this direction to produce a magnetic field going in the opposite direction as that of the solenoid.